Welcome. This is the first topic in the last unit of the course, Unit 3. And Unit 3 is all about quantum physics and nuclear physics. And it's kind of divided into two halves. So in this first set of topics, topics 1 to 3, we're going to be talking about the quantum side. And then in the final set of 3 topics, from 4 to 6, we're going to talk about the nuclear physics part of Unit 3. So the first topic, we're going to split into 2 parts. So this is going to be part 1, then there'll be a part 2 where we'll actually look at some sample problems from old publics. So this is the theory behind that stuff. This is the information you need to know in order to be able to answer questions in Unit 3. So let's get started. You may remember from Physics 2204, there was a little bit of talk in that about the nature of light. And there was a lot of debate over whether light was a particle or light was a wave. And towards the end of the 2204 unit, their unit number 4 in Physics 2204, it was kind of proposed that based on the properties of light that had been discovered at that point, primarily things like diffraction of light, interference of light, and polarization of light, all those things tended to point to a wave theory for light. So the wave theory kind of got accepted up until the early 1900s. Because what happened then was when some guys like Max Planck and Albert Einstein and names like that started to look into it a little bit more, they found some conflicting information, I guess you'd call it. They found some problems with the classical or wave theory of light. And I'm going to summarize these here because sometimes that does show up in some form on the public, not usually as a long answer question, but often it shows up there as maybe a multiple choice, something like that. So let's take a look. There are 4 main problems with the traditional model of light, the wave model that was accepted at the time. And the first one was, if we think about waves and we think about water waves, a water wave with a large amplitude obviously can do more damage than a water wave with a small amplitude. Okay, and here in Newfoundland we've certainly seen lots of evidence of that. Big waves can do a lot of damage. So if light is a wave, it would seem reasonable to apply that to light and say that the energy of the light would depend upon the amplitude of the light wave. In other words, the brightness. However, that is not observed for light. That doesn't happen. In other words, with light, the amplitude doesn't seem to affect the energy. It doesn't seem to affect the damage it can do, if you want to use that analogy. So there's strike 1. Okay, so the actual nature of light became an issue too. And if you think back to Physics 2204, when Thomas Young performed his double slit experiment, and things like Poisson's bright spot had been discovered a little while before that, it was decided that light had to be a wave because waves are the only things that show diffraction and interference patterns. Okay, it was thought that particles couldn't do that. However, it was later discovered in the early 1900s that particles like electrons could produce interference patterns. Okay? Electrons fired through a small opening could also produce an interference pattern. So particles, under the right conditions, can also produce diffraction and interference. So there goes the big idea that light had to be a wave because of interference. Not so. Apparently particles can show interference too, so strike 2. Then it was also discovered around the same time, again early 1900s, that in the certain circumstances, under the right conditions, when light struck certain metals, metal surfaces, electrons could be bounced off. In other words, electrons were knocked off the surface by nothing other than the light itself. And we call that phenomena the photoelectric effect, and you did study that later in Unit 3. Anyway, in this situation, when that happens, that's almost like collisions, right? Conservation of momentum. Okay, when the photons of light strike the surface of the metal, they seem to be able to bounce electrons off by colliding with them. So again, particle, light was behaving more like a particle in that case. Waves shouldn't be able to do that. Waves have no substance. Waves are just a means of transferring energy from one place to another. They shouldn't have momentum. They shouldn't be able to collide with things, etc., etc. So, third strike. And then there was another one, and we're going to talk about this a little later on, actually, in Topic 3. But the view at the time was that light was emitted because electrons lose energy and fall into lower orbits around the nucleus. Okay, and that was pretty widely accepted. In fact, that is the case. But if that lost energy comes out as light, then wouldn't the electrons eventually go low enough to actually crash into the nucleus? That didn't happen, because if it did, atoms wouldn't be able to hold on to their electrons at all. Nothing would be stable. And obviously matter is stable, or we wouldn't be here. So there was no theory to explain exactly what was going on in that atom when light was emitted. They were pretty sure it was because the electrons were losing energy, but why weren't they actually crashing into the nucleus eventually? Okay, why wasn't that happening? So there are 4 big problems with the old wave theory of light. So that meant whenever you start finding problems like that, and this is what the scientific method is all about, as soon as you start detecting problems with the theory, then it's time for a new theory. So a new theory of light was developed, and that's what we call the quantum theory. So let's take a look at the main ideas behind that. So in the early 1900s, we got a few people like Max Planck, very well-known name in this era of physics. Albert Einstein, probably one of the best-known names in science, period. There's not too many people that haven't heard of Albert Einstein. Anyway, they said maybe we're looking at energy the wrong way completely. Okay, here's the classical idea of energy right here. Classical idea of energy was energy can have any value. Let's just imagine a box sliding up and down a ramp. That box can have any amount of gravitational potential energy anywhere on that ramp. Okay, the higher we push it, the more energy it has. So there's a continuum of energy. But what Planck and Einstein said, and they both had basically the same idea at around the same time, so sometimes one gets credited for the idea, sometimes the other one gets credited for it, but they both pretty well developed the same theory at almost exactly the same time. Anyway, Einstein and Planck said maybe when in terms of atoms and electrons and light, maybe there's a better way to look at energy. So Planck in particular proposed the quantum idea of energy. And you can think of that as steps. Okay, so now this box can be here on this step, here on this step, or here on this step. It can't be anywhere in between. It's not magically going to stop halfway up the step. So now we can only have certain amounts of energy. And that's the best way to visualize what the quantum theory is all about. That's really what quantum theory is all about in very simple terms. Okay, on the ramp, the box can have any amount of energy, but on the steps, you can only have certain specific amounts of energy, and that's it. Okay, if you count the very bottom and the very top, we got 1, 2, 3, 4 steps. 4 specific amounts of energy that we can have, and nothing in between. Okay, it's possible for the box to stay at one energy level and not go anywhere, unless someone gives it a push and knocks it down to the other one, or someone lifts it up to the next one up. Okay, whereas with this one, that box can slide up and down. You let that box go, that can slide all the way down to the bottom. It's not stable. But this guy here, this is pretty stable. Once you put that box on a step, he's going to stay there until you do something to it. So that's the quantum idea of energy. So I hope that makes it a little more clear for you. So Max Planck was the one who coined the term quanta. So quanta is what he called these discrete or specific amounts of energy. Okay, so his idea of quanta was really good at explaining why light sometimes acted like a wave and sometimes it acted like a particle. Okay, and that's what this is all about. Because light is kind of a little of both. Okay, it has some properties of particles, it has some properties of waves. It's kind of like a hybrid. It's a little bit of both things. Anyway, each quantum or each quanta of energy that's emitted from an atom or with light, whatever, we can think of it as a tiny packet or a particle. We can think of individual photons of light as particles. When they strike something, they act like a particle. But as they're moving, they travel like waves. Okay, that's the thing. That's the unique thing about photons and electrons and those types of things. So the scientific name for this tiny packet, we call that a photon. So a photon of light is just a small packet of light energy. Okay, so when Planck started experimenting with this idea, okay, he concluded that we couldn't anymore try to say that the amount of energy in a light wave or in a photon depended on its amplitude, because brighter light didn't seem to have any more energy than dimmer light. So the amplitude didn't seem to have anything to do with the energy. However, Planck said this: if the wavelength decreases, then the energy increases. And if the wavelength decreases, the frequency also increases. So we can also say the frequency increases, the energy increases. So for example, blue light has a wavelength of somewhere around 450 nanometers. Violet light, which is a little further along the electromagnetic spectrum, is 410 nanometers. Therefore, photons of violet light would have more energy. And if you go a little further to ultraviolet, okay, UV is better known as, and we know very well what UV effects, how that can affect us when we stay out in the sun too long. It gives you sunburn. It has more energy than the visible light. Okay, so because they have a shorter wavelength, they also have more energy. As wavelength decreases, frequency increases, so we can also say as the frequency goes up, so does the energy. Okay, in fact, Planck actually came up with an equation. So if energy is proportional to frequency, then we can say, by putting in a constant, a proportionality constant, we can say E equals h times f. That formula is actually on the formula sheet. E equals hf. That's the energy of a photon. And that h, that constant, is called Planck's constant in honor of the man who calculated the value of it. Okay, he actually measured the energy of photons, knowing the frequency, and figured out experimentally what this value of h was. Now it's been refined a little since, but this is the value that's given on your data sheet that you will get with the public exam. Okay. Often the Greek letter gamma is used like this. Sometimes you might see this. Okay, it looks like a fish standing on his nose. That's the gamma symbol. A gamma is often used to symbolize a photon. Often. So now let's think about the universal wave equation. And you should remember that from Physics 2204. V equals F times lambda. And if V equals F times lambda, then F equals V over lambda. But because we're talking about light here, we can say C over lambda instead. Okay, C over lambda instead of V over lambda. So that means we can substitute C over lambda in place of the F in Planck's equation. So this equation would become, instead of E equals h times F, it can become E equals h times C over lambda. Okay, C over lambda. replacing the F. Because often you're given the wavelength instead of the frequency. In fact, I would say in the majority of problems that you're asked to do on the publics, it's usually this formula they're using instead of this one. So while you're given this one, you do need to know this one too. But if you can remember this wave equation, it's an easy substitution. Okay, so keep that in mind. So around the same time that we were talking about energy of photons and things like that, the whole concept of black bodies was discovered. And a black body is essentially an ideal thing. It doesn't actually exist. A perfect black body doesn't exist in nature. Because a perfect black body would be an object that absorbs every bit of radiation that falls on it, including visible light. Hence the name black body, because it would be black if it absorbed all light. Okay, so, but it would also absorb every other type of electromagnetic radiation, including radar, ultraviolet, radio waves, anything. Nothing would reflect off of it. It would absorb them all. And it turns out, though, that objects which are excellent absorbers are also excellent emitters. So a black body, or something that is very close to the perfect black body, would emit radiation much more efficiently than other objects would. All right? Now, any opaque object, and by opaque we mean it's not transparent, it's not see-through. Any opaque object that has a temperature above absolute zero radiates photons of some sort. Sometimes it's visible light, sometimes it's not. This effect is known as black body radiation. Okay, so try to remember that. For example, you can feel the heat from a fire. You can feel the heat of the sun without touching it. If you touch them, you get too close, you get burned. So you can feel that, though, because the spectrum of radiation coming from those is a continuous spectrum, almost like the colors of a rainbow. Okay, but they're not all the same intensity. For example, the hotter the object gets, the more it shifts to one end of the spectrum versus the other. Like hotter fire, for example, is a different color than a cooler flame. So when you turn on the element on the stove, for example, if you look at it, okay, before you turn it on, it's fairly cool to the touch. But when you turn it on, it starts to get hotter and hotter, and eventually it gets so hot that it actually glows red. So what's happening is, now a lot of the energy being released is visible light. Okay, it's become visible light. And it's also releasing a lot more infrared. That's why you can feel the heat now. So we can actually show that by drawing a graph. Right? For example, here are 3 different graphs drawn for the same object that's radiating energy. So for example, let's say this is your stove element. Okay? When it's just turned on, it's just starting to get hot. Okay? It actually starts, the peak is down here in the heat. So it's not giving off very much light yet, barely visible. But as soon as it starts to get very hot, notice how the peak is shifting up towards visible light. So now you'll notice it's giving out a lot of visible light. Right? Here's the boundary, for example, for visible light, just to the left of this dotted line. Right? See, we see red right here. Red is the longest wavelength of light that we can actually see. So a lot of the energy of that one is actually in the visible range. When it gets extremely hot, you'll notice now it's got all the colors of the spectrum, everything from red to violet. When that happens, it actually glows white, because now it's emitting all the colors. It's emitting all the colors. It's also emitting now some UV. So when the object gets hot enough, like the sun, it will emit UV radiation, and you can actually get a sunburn from it. So the important thing to note here is that, number one, the graph gets higher, so the intensity of the radiation that's getting emitted increases as the temperature increases. Keep that in mind. But the peak of the graph also shifts to the left. In other words, the peak shifts to a shorter wavelength or a higher frequency, and therefore more energy. Okay, there is more energy in these graphs, but it's not because of the intensity. It's because the peak now is at a higher frequency. That's why. So that's what a black body curve looks like for any object. And the hotter you make it, the more you shift that graph to the left and up. Okay, so try to keep that in mind. That's black bodies. Then we come to the photoelectric effect. And the photoelectric effect we've already mentioned. Okay, we mentioned the photoelectric effect as one of the problems with the wave theory of light. Okay, because when photons strike a metal plate, electrons can be bounced off. Okay, that was or could not be explained using wave theory. Okay, unless there were some kind of particles in that wave, it shouldn't be able to do that. But it turns out that the photoelectric effect only occurs when the photons have enough energy. That makes sense. If they don't have enough energy, just like if you don't have enough energy to lift something, it's not going anywhere. Okay, same idea. So since energy of photons depend on their frequency, then obviously low frequency photons would probably not cause the photoelectric effect to occur. However, the other interesting one is this, that changing the intensity or the brightness of the light has absolutely no effect on whether or not the photoelectric effect will occur. None. Okay? It's only the frequency that's important for determining whether or not it will occur. But changing the intensity does have an effect. It doesn't affect whether the photoelectric effect occurs or not, but when the light gets brighter, more intense, we do get more electrons being bumped off. In other words, the current would increase. But it wouldn't affect whether or not electrons would be ejected at all. Okay, and that'll make a bit more sense when we talk about it now in some of the problems that we're about to do in part 2 of this topic, this lesson. So let's go on and take a look at what this is all about. So if there's a certain minimum that's needed, then it makes sense to say that there is something called a cutoff, or sometimes called a threshold frequency. In other words, remember, there's a certain frequency that's needed in order to have enough energy to bump electrons off. We're going to call that the threshold frequency. If the frequency is below that number, no electrons are bumped off the surface. In other words, no photoelectric effect. And we'll do some calculations based on that in the second part. Okay, in fact, if the frequency of the electrons is exactly equal to the threshold, the electrons just barely get bumped off anyway. A scattered one, but not very many, and they have hardly any energy. They're only barely knocked off the surface. Very weak. But once we go past that threshold, the current right away jumps to a maximum value. And that maximum value would only change if we increase the brightness of the light. Only if we increase the brightness. And again, we'll talk more about that when we get to it as well, when we get to some things. So, this minimum energy that we need, we're going to call that the work function. And we're going to use an analogy here. Let's say you're playing soccer, and you're trying to kick a soccer ball, but you're on the beach and the ball is half buried in sand. So if you're going to kick that ball out of the sand, obviously you're going to have to kick it hard enough to move it. Because if you only kick it lightly, it's going to stay stuck. It's going to stay stuck in the sand. So your foot that's coming at the ball, its energy is going to be split two ways. One part of the energy is going to loosen the ball out of the sand, and then whatever's left over is going to give the ball kinetic energy to move. Okay? But if we don't have enough energy to get it into the sand, the ball's not going anywhere to begin with. Okay? So that's kind of like the photoelectric effect in a lot of ways. This is very similar. The energy of a photon that's coming in about to hit the metal is calculated like this, either HF or HC over lambda, depending on whether you're given the frequency or the wavelength. So we use that to calculate the energy of the photon. And there's that gamma symbol right there. So again, that gets split two ways. Some of that energy is actually used to free electrons. In other words, to bump electrons off the surface. Okay, that's what some of the energy does. We call that the work function. That is the minimum energy that we need to bump those electrons off. And then whatever energy is left over is going to provide those freed electrons with kinetic energy. Okay, so it's two parts. First of all, we have to free the electrons to begin with. We call that the work function. And then whatever's left over is going to cause those electrons to move with kinetic energy. Okay, so essentially then, this is the formula. E gamma, in other words, energy of the photon, which is HF or HC over lambda, is equal to WO plus EK, the kinetic energy of the electrons. That is Planck's equation for photoelectric effect. Okay, and like I said, this was developed by Planck and Einstein at around the same time. So sometimes it's Planck's equation, sometimes it's called Einstein's. Okay, the credit is kind of mixed there. So that is the concept of the photoelectric effect. Now you might wonder, how did they know? How did they know these electrons were coming off? How did they know how much energy they had, etc., etc.? Well, they designed a very ingenious apparatus. Yeah, it looks like this. And this diagram, by the way, comes straight out of your textbook. Okay, what it was, they had a collector tube right here with no air in it. And we had a metal plate right here with a tube for the light to shine through and onto the metal plate. When that happened, electrons would get bumped off. Now these electrons, because there was a positive plate over here, would end up getting pulled towards that positive plate. Okay? And this actually provided a stream of electrons to replace the ones that were being bumped off by the light. So they would travel the gap and then go around the circle. And we could actually measure how much current was being produced. If we want to know how much energy those electrons have, there's a very simple way to do it. There's a very simple way that can be done. And here's the way they did it. What they can do is this power supply down here can be reversed. And if that happens, if you reverse this power supply, all of a sudden this plate becomes negative. And if this plate becomes negative, it's not going to attract those electrons anymore. It's actually going to repel them. So all we got to do is figure out how much voltage we have to apply to this plate in order to stop these electrons from moving. In other words, to cancel out their energy. Okay, and that's what we do. So we find something called the stopping potential, and you're going to see that word from time to time, or that term I should say, on public exams. Stopping potential, or V-stop. And it works like this. If the anode becomes positive, right? If the anode is positive, which is what it was initially, the electrons are attracted to it and current starts to flow. But if we reverse the potential and make that same plate negative, then the electrons are going to be repelled now and the current will stop. So we want to know what is the minimum voltage that we need to make that happen. So in other words, for each electron, and E is the charge on an electron, the stopping potential would be energy. Electric potential energy would equal E times V. And you may remember that from Unit 2 of the course. So I'm going to say that the energy required to stop these electrons is equal to E, which is the charge on an electron, times V stop, the stopping potential. That formula is a very important one. However, it is not given on the formula sheet. So you're going to need to remember that. That's a very important one to remember. So if that's the energy that's needed to stop them, then that tells us that must be the kinetic energy they had in the first place. That's how you can determine how much kinetic energy the ejected electrons, or sometimes called photoelectrons, actually have. Okay, and we're going in part 2 of this lesson to go and look at some actual questions from old public exams. So that ends the theory part of it. So to see some of this stuff in action and what types of questions you're going to see on the public exam, then please view part 2 of Unit 3, Topic 1.